So I will say the important topics in synchronization where you need to actually concentrate. The one of the very important topic is semaphore is very, very important. But other than the semaphore, also we'll discuss the what is mutual exclusion, progress, and bounded waiting, and along with the PYQ. Okay. So today in the first session we'll do this one, and let's see up to what extent we can go with this particular topic. And after this topic, I'm planning to take memory management topic, because these are the two topics where I'm finding that students have some doubts. Okay, so let's start. What is synchronization? What is synchronization? Okay, so please tell me one thing. What is synchronization actually? About the synchronization, I will say one thing. Okay, see here. Processes is classified into two parts. The one is independent process, and other one is cooperative process. Okay, and don't worry, we'll discuss because a little bit slowly. The reason is very simple, because the most of the time students are getting confusion in this topic. Okay, fine. Hope you have covered this topic, but still I will suggest you to see once again, because this is the topic where you are finding the difficulty. Okay, fine. So CP scheduling and file system, these are the easy topics. So that's why within 4 hours, I don't want to waste your time discussing such kind of topic. But still, if you want, you can recommend me after the completion of this particular two topics which I have decided, like synchronization and memory management. Okay, so better to concentrate, because it is a 4 hours class, so better to concentrate on the main topic. Let's see this one: cooperative process and independent processes. What is the meaning of cooperative processes? Cooperative processes are such kind of processes where at the time of execution they may affect on each other. Once again, at the time of execution they may affect on each other. The best example is what's a producer consumer problem. The best example is what's a producer consumer problem, where both are affecting on each other. So that's why we are getting the data inconsistency issue. So what is data inconsistency issue? We know, we have already discussed earlier. Okay, hope you have learned this one. But still, if you don't know data inconsistency, I will say you one thing. See here, I'm going with what's a 2 plus 4. What is my expected result? 6. But I'm getting other than the 6. I'm not getting the 6, but I'm getting 8, 10 like that. Okay, fine. I'm not getting error, but I'm getting the value, but that is not a correct value. That is data inconsistency issue. Okay, fine. So if two processes are affecting on each other at the time of execution, such kind of process are we are saying cooperative processes or coordinating processes, also another name for this one. But I will say one thing. So why they are affecting on each other? The answer for this one is not. They may be sharing something. Okay, it is something like this here. If two friends are there who are sharing this bike, okay, one day what happened, sir? Mr. A and Mr. B. Mr. A want to go in this direction, Mr. B want to go in this direction, but at the same time. So don't you think that they will fight with each other or not? Yes. Why? Reason is what, sir? Because of this common bike. Okay, because of this common bike. If there is nothing is common, sir, will they affect on each other? Answer is no. Such kind of process is called what's an independent process. Okay, fine. Now, to control this cooperative process, sir, we have some mechanism which is called IPC, inter-process communication. Okay, fine. And the inter-process communication is classified into two parts. The first one is shared memory, and the second one is message passing. Okay, shared memory means what, sir? This is a main memory. Process P1, shared memory is there. Process P2 is there. Okay, fine. Process P1 is something is keeping inside the shared memory, and process P2 is consuming from that area of memory. Okay, so this is main memory. Message passing means what, sir? Two processes are communicating with each other through message passing. But the best part is what, sir? No need to concentrate in this area. Based on your syllabus, sir, you have to concentrate in this area. This is the best part. You have to concentrate here. Okay, fine. So let's see what is the other thing. What is the meaning of synchronization? Okay, what is the meaning of synchronization? We'll see. Most of the time we are getting the scenario of the synchronization, but actually we are not catching the what is the meaning of synchronization actually. Okay, fine. So try to understand this one. I will give some general example to explain you this concept. Okay, and I will discuss some algorithms also in this. It doesn't mean that I am discussing only semaphore and some problems. No, I will discuss some algorithms also, and after that semaphore and some problems we will solve PYQ, and after this we'll complete our synchronization. Okay, fine. But before this one, we need to understand that what is exactly meaning of synchronization. Try to understand this one. See, this is what, sir? White paper. Okay, white paper. The multiple one day I kept what I have done, sir. One day I kept this white paper on the table. I am asking students, please come and write about yourself. And whichever person is writing about himself, and I will allow that person to leave class. Okay, he can be on leave. Okay, fine. So offer is very attractive. So high chances are there all the students will come at the same time. Okay, fine. Like person 1, person 2, person 3, person 4, person 5, like this, they are coming at the same time. And they will start writing on the same paper. So they are writing their name, but I'm not taking what name they are writing or such kind of things. Okay, fine. I'm saying that let's assume this person is writing, P1 is writing x equals to 10, and P2 is modifying to 20, and P3 is modifying to 30. P1 is thinking that the x value is 10 and the P2 is thinking that the x value is 20, but the real value of x is what's the 30. So that means what, sir? We are actually getting some problems here. We are getting some problem. Okay, fine. The next one, the question will come, sir, how to overcome this problem? How to overcome this problem? So once again, this is white paper. To overcome this problem, sir, we require some algorithm or synchronization mechanism. Algorithm, I will say here. Okay, fine. Like here, I will say, sir, allow person to write about themselves based on the rule number. Like rule number 1 is coming and writing about himself or herself, or rule number 2 is coming, writing about herself, and rule number 3 is coming, writing about herself. Okay, fine. If rule number 1 is writing, sir, after the completion of the writing is passing this pen to roll number 2. Once this roll number 2 is getting this pen, now he's getting signal that his turn came. And once roll number 2 is completing its task of writing, and he will pass this pen to what's the roll number 3, like this. So based on this one, sir, based on the algorithm, don't you think, sir, we are creating the effective communication among the persons or not, sir? Answer is yes. This effective communication is called what's a synchronization. Remember this. Okay, this effective communication is called what's a synchronization. So I will take one example. This is just general example to give the scenario what exactly happening in the context of the synchronization, because this kind of things are not there in the book. So that's why people get lots of confusion in this. Okay, fine. So that's why I decided that better to take some tough topic instead of discussing the CP only. Okay, let's see this one. This is a critical section. What is the meaning of critical section, sir? It is a shared part of a program. Like in producer consumer, we are declaring count and buffer globally. That is what that comes under what's a critical section. Okay, fine. If something you are declaring globally, so high chances are there's a multiple process can access at that same time. So such kind of things called what's a critical section. Okay, fine. Now, sir, what exactly happening technically? Multiple processes are trying to execute this critical section at the same time. And because of this, we are getting one problem which is called data inconsistency. Data inconsistency. So this is problem. What is the data inconsistency? Just I have shared you that expected result you are not getting. Okay, fine. So let's see how to overcome this issue. To overcome this issue, we have some algorithms. We have some algorithms are also called as synchronization mechanism. Synchronization mechanism. What is that synchronization mechanism, sir? It can be Peterson's solution, it can be strict alteration solution, it can be semaphore, it can be monitor, it can be anything. I'm not saying which is a specific one. I'm saying that algorithm. Okay, fine. Next one, sir. So if any process is trying to enter inside the critical section, so what is the difference between these two cases, sir? Here there is no barrier to access the critical section, but here, sir, barrier is there to access the critical section. This algorithm is barrier actually. When process P1 is trying to enter inside the critical section, this algorithm will check whether inside the critical section any process is there or not. Right now it is no one is there. This algorithm will allow this process P1 to enter inside the critical section. But once the process P1 is there inside the critical section, at this point of time, if process P2 is trying to enter inside the critical section, this algorithm will not allow that process. Okay, fine. Okay, and because of this, what is happening, sir? At a time, how many processes are writing inside the critical section? 1. So we are overcoming this issue because of this what's our algorithm. Okay, so don't you think, sir, because of this algorithm we are creating the effective communication between these two processes or not, sir? Yes, sir, because if one is there inside the critical section, other has to wait. So this kind of communication we are creating because of this algorithm. So this effective communication which we are getting because of algorithm is called what, sir? Synchronization. It's called what, sir? Synchronization. Okay, chaliye. So main part. Now try to understand this one. Doubts, where the students are getting doubts. Sir, where we are getting the doubts, sir? You are getting doubts. If I am asking you, you can leave your answer in the chat. Okay, fine. Now please tell me, in synchronization, where we need to focus, sir? In critical section or algorithm? Where we need to focus, sir? Can anyone? I'm giving you 10 seconds. If you're not typing, okay, anyhow, I will say, don't do. Because we don't have much time. Okay, fine. Where we need to focus, sir? Critical section or algorithm, sir? Many students think, sir, we need to focus on critical section. But I will say no. Inside your critical section, problem is there. To solve that problem, we require the algorithm. We require what, sir? Algorithm. But we have the so many algorithms. Which algorithm we need to use, sir? We need to test the algorithm. Which algorithm is good, which algorithm is bad. Sir, how you will test this algorithm, sir? To test this algorithm, sir, we have some basic requirement like mutual exclusion, progress, and bounded weighting. If any algorithm is satisfying all these three requirements, then I will say this algorithm is good. Otherwise, I will say this is not good algorithm. So what exactly happening in the context of the synchronization, sir? If you are observing closely, inside the critical section, we have the problem. To solve this problem, sir, we require what, sir? Algorithm. Okay, fine. Now we are checking the algorithm. We are taking one algorithm and we are checking that whether this algorithm is satisfying mutual exclusion or not, progress or not, bounded weighting or not. These are the things actually you are doing in the context of the synchronization. See, I'm taking the Peterson solution, but what actually I'm doing, sir, inside the Peterson solution, sir, I'm testing whether this algorithm is satisfying mutual exclusion, progress, and bounded weighting, such kind of things. Getting this idea or not? So hope you are getting this. Why we are checking that? Okay, fine. So because we know, sir, if algorithm is good, it will solve my problem. If algorithm itself is a bad, sir, then my problem remains same, but it will add some more problem. This is a problem. If you are getting some pain in your stomach, then where you are concentrating, sir, on your stomach or on the medicine, sir? Medicine, obviously, because if you are concentrating on stomach, it will not solve your problem. You know, sir, inside the medicine, your solution is there. So that's why whenever you are buying some medicine, sir, you are checking the ingredients. Okay, so if ingredients, because you know if ingredients are good, then it is solving your problem. Otherwise, problem remains same only. Okay, fine. So here also, sir, as I said, that to check any algorithm, we have some basic condition. Like here in this example, if you are asking me, I will say my pen should be in good condition, my paper should be in good condition, and I will say some other thing like if roll number 1 is writing, then roll number 2 should also present inside the class. Otherwise, what will happen, sir? After the completion of 1 writing, then it will search for the rule number 2, it will consume lots of time. Okay, fine. So such kind of basic requirements are there. So overall, sir, what actually we are doing in the context of the synchronization, see here, there is no effective communication among the process. Because of this, we are getting some problem. To solve all these problems, sir, we require algorithm. But we have so many algorithm. The question will come, sir, which algorithm I need to choose? To test that, which algorithm is good for you to solve the issue of this data inconsistency, we have some basic requirement like mutual exclusion, progress, and bounded weighting. Okay, we have some basic requirement to check all these things. Okay, so that means what? To solve the critical section problem, we are checking the algorithm, whether this algorithm is satisfying all these three things. Okay, fine. Chalo, next we'll check, sir. Let's say this one. Let's say this one. Producer consumer problem. Actually, this is buffer and okay. So anyhow, we have discussed all these things. Okay, no need to discuss once again, but I'll give the brief idea about this one. But the main concept I will discuss where this creating the problem actually. Okay, now please pay attention to this. What is the basic functionality of the producer consumer, sir? 0, 1, 2, 3, 4. This is buffer. What is the basic functionality, sir? Producer is keeping some element inside the buffer and consumer is consuming element from the buffer. This is the basic functionality. Okay, fine. So let's say, sir, I will give you the one case. Has defined n equals to 5. What is answer? 5. Okay, fine. Int count equals to 0. Count you are using to indicate number of elements inside the buffer. So right now, since no element is there inside the buffer, that's why count equals to what's 0. Okay, fine. Buffer n. What is the answer? 5. So buffer has how many partitions, sir? 5 partitions are there. Okay. Now, next one, sir. Okay, let's see. Producer. So producer has its own variable like item P and invariable. Item P and invariable using by the producer. Invariable is using by the producer to point to the buffer separately. Okay, fine. So I'm writing this code under the while one. Okay, fine. Why? Because I want to execute this code again and again, again and again. How long we don't know actually. Okay, fine. So let's see what will happen, sir. This is a library function. Produce item P. So producer is ready with what's some library function to generate some item. But sir, please tell me, can you imagine that producer will keep the element inside the buffer blindly, or before checking the element, before keeping the element inside the buffer, producer will check the status of the buffer? Answer is what, sir? Obviously, it will check the status of the buffer. If buffer is freely available, then it will keep the item. If buffer is full, then producer need to wait. Okay, producer need to wait. Let's see, sir, what will happen. What is count, sir? 0. N value is what, sir? 5. Is 0 equals to 5, sir? Answer is no. So whenever this condition is becoming false, execute the next statement. Okay, execute the next statement. What is the next statement, sir? Buffer in. On the 0 slot, keep the item whatever you have generated. Let's assume that I am saying item P as A. Okay, fine. Now I'm incrementing this in value to the next slot. Okay, fine. And I'm incrementing this what's count value to what's 1. Okay. Why I'm taking the mod operator, sir, here? Because see, after keeping the 5 element inside the buffer, producer will try to keep the 6th element on the 0th slot, because chances are there when producer is keeping some element, at the same time consumer can also consume the item from the buffer. So maybe chances are there this slot can be freely available if consumer is consuming the item from the buffer. Okay, so that's why, sir, we are using the mod operator. After keeping the 5 element, producer will come back to here. If it is freely available, it will keep the 6th element on the 0th slot. If it is not freely available, then it will get blocked. Okay, fine, which makes sense. Let's say, sir, this one. After keeping one element, it is incrementing this count value. Next one. Now let's see what consumer does. This is a consumer. 1, 2, 3, 4. Okay, fine. So consumer has his own variable. Out variable is using by the consumer to point to the buffer separately. Fine, Chelly. While one, what is count, sir? Count right now it is 1, because see, if you are checking earlier value, it is 1. Okay, fine. So one element is there inside the buffer. Now consumer is coming, sir. Count value is what, sir? 1. Is 1 equals to 0, sir? Answer is what, sir? No. So this condition is becoming false. Now from 0 slot of the buffer, copy the item from 0 slot of the buffer and inside the item C. So inside the item C, I am keeping what, sir? A element inside the item C. Now incrementing this out value to the next slot. Okay, fine, sir. Now after consuming the item from the buffer, we need to decrease this count value. What is the count value, sir? The 1 is becoming 0. Okay, fine. Now process the item. Once again, I am taking some library function support to process the item. Okay, understood this? Okay, so in this way, producer is keeping one element inside the buffer and consumer is consuming that element from the buffer. Okay, fine. So this is a case 1. Actually, I will say, sir, it is a case 1. Now I'm taking the case 2, sir. Case 2. Let's see what will happen in the case 2. In case 2, I am starting with the consumer and buffer is freely available. 0, 1, 2, 3, 4. Okay, fine. Let's see what will happen, sir. What is count value, sir? 0. Okay, fine. Now consumer is coming, sir. Now is 0 equals to 0? Answer is yes. Then consumer will go for the busy waiting. Sir, we have one doubt, sir. If we have actually whatever we know about the while condition, because most of the time students will ask him, whenever this condition is becoming true, you are executing the next statement. Actually we are executing the next statement, but whenever it is becoming false, we are coming out from the loop. But you are taking vice versa, sir. Whenever condition is becoming true, you are saying that it is busy waiting. What is the meaning of this one, sir? See here, after the while semicolon is there. Whenever you are writing the C language programming, sir, you are not writing such kind of programs where the two processes are communicating communicating with each other. So that's why you don't know the significance of the semicolon. What is the meaning of this one, sir? The meaning of this one is what, sir? While one, do nothing. So that means whenever this condition is becoming true, this empty body you are executing again and again, again and again. How long, sir? Until unless this condition is not becoming false. Okay, fine. So that's why, sir, whenever this condition is true, you are executing this empty body. Exactly this situation is called busy waiting. And whenever this condition is becoming false, which we have already seen earlier, what was happening, sir? I was executing the next statement. Why? Because you are coming out from this sleep. Okay, that's why you're executing the next statement. But anyhow, sir, consumer is there inside the busy waiting. Let's see what will happen with the producer. Producer. Producer is coming, sir. Count ka value kya, sir? What is the count value right now? It is 0. Okay, fine. Let's see this one. Producer. Produce item P. So producer is ready with the item. Now it is comparing this value. N equals to 5 and count value equals to what, sir? 0. Is 0 equals to 5, sir? Answer is no. So whenever this condition is becoming false, execute the next statement after this one, sir. Which is the next statement, sir? Item P in variable is what, sir? At the 0 slot. Okay, fine. In variable is what, sir? At the 0 slot. So on the 0 slot, I am keeping what, sir? First element. Next, increase this in value. So from 0, so it is increasing to 1. Now increase count value. But once you are incrementing this count value, sir, what will happen? Because the count is a shared variable. See, count and buffer is a shared variable. Actually, they are acting like critical section. They are the critical section actually. Okay, fine. So if any one process is performing any operation, whether it is incrementation or decrementation, the effect is there at the both side because it is a global variable. Okay, fine. Let's see this one. So now earlier it was what's a busy waiting. Now consumer, whenever it is getting chance, it is executing this one, sir. But right now we are finding count value as 1. Is 1 equals to 0, sir? This condition is becoming false. Execute the next statement after the while. Now, sir, buffer out. That means out variable is out variable C. Producer kept one element, no, sir, inside the buffer here. See, this element I am taking here and increasing the count value also. Okay, fine. Chali. Now, so buffer out. So inside the item C, we are capturing what's A and increasing this out value to the what's next slot. And next one is what's decrease this count value to 0 and process the item C. That means what's we are taking some library function support to process the item. So in this way, sir, if you are observing, whenever consumer is becoming illegal, we are in a position to stop to the what's consumer, and producer is giving chance after keeping one element inside the buffer. Same thing vice versa is also correct, sir. Vice versa is also correct. What is happening the vice versa, sir? Vice versa. See, whenever becoming producer is becoming illegal, let's assume this 5 elements are there inside the buffer. Okay, try to imagine this one because I don't want to explain once again. Same scenario. It is a boring procedure. Okay, fine. But anyways, if 5 elements are there, so count value is 5. Producer is coming here, checking this one is 5 equals to 5. Yes, sir. Answer is true. So it will go for the busy waiting. Obviously, for the 6th element, producer is illegal. That's why we are in a position to stop to the producer because he already kept the 5 element and total buffer is full. Now consumer will come. Consumer will come and it is comparing this one, sir. Count value is what's the 5? Is 5 equals to 0? Answer is what's the no. So it is consuming the next element, okay, and decreasing the count value. Okay, so it is consuming the first element and it is decreasing the count value. Once the count is becoming 4, once the count is becoming 4, what will happen, sir? What will happen, sir? This condition is becoming false. This condition is becoming what's the false. Now producer will come to the 6th slot and it will keep the item. But anyway, even try to imagine this one. What is the main thing, sir? Whenever, whether it is a producer or consumer, whichever process is becoming illegal, sir, we are in a position to stop that process. The main fund of this one is what, sir? Okay, fine. Chali. The next one, sir. Next one. Come back to the main point, sir. Come back to the main point. Till now, sir, whatever we have discussed about the producer and consumer, okay, we are finding, sir, we are not getting any issue here actually. Okay, fine. Why we are not getting any issue, sir? Because most of the time I'm taking the process one after the other. I'm not taking a situation where a shared resource is executing, like count variable is executing by producer and consumer at the same time. At the same time. Just wait for 2 minutes because Azan is going on. Okay, I will continue after 2 minutes. I will be here only. Okay. So we'll see a case where shared resource is accessing the producer and consumer at the same time. What is the shared resource here? Count variable. Okay, fine. So let's assume this. Right now, initially count values what are I am taking as 3. So that means how many elements are there inside the buffer? 3. Okay, fine. So let's see what will happen. Producer is executing the first instruction. What is first instruction, sir? Load count value into the RP register. So we are loading the count value into the RP register. So that is 3. Now producer is executing the second instruction. What is the increment RP? So that means what's that is 4. Okay, fine. Now before executing the third instruction, sir, we are preempting the process. The next one, consumer. Consumer is executing the first instruction. What is first instruction, sir? Load count value to the RC. Okay. So what is the count value, sir? Don't say 4. 4 is there inside the RP register. It's still inside the main memory. Count value is 3 because we have not yet updated. We have not yet executed the third instruction. Getting this idea? Fine. It is 3 only. Fine. Next one. Decrease this RC value to what, sir? Or 2. Fine. Now, sir, before executing the third instruction, I'm preempting this process. Now that means what, sir? Consumer also executed the second instruction. Now I'm giving chance to the producer. Producer is executing what's the third instruction. What is third instruction, sir? Whatever the value is there inside the RP register, please store to the memory. So that means what, sir? We are storing to the memory as a 4. Okay, fine. Now producer has completed the third instruction. Now consumer is executing the third instruction. What is the third instruction, sir? Whatever the values there inside the RC register, please update to memory. So now consumer is coming and it is updating to the what, sir? 2. So final result, what actually you are getting, sir? 2. What is our expected result, sir? See, if initial value of count is, if I have taken 3 means what, sir? Let's assume this producer has kept one element inside the buffer and it has incremented to 4. Okay, fine. And consumer has consumed one element from the buffer and it has decremented this count value to what, sir? 1. So once again the value is becoming what, sir? 3 only. Our expected result is what, sir? 3. But what actually I am getting, sir? I am getting 2. So this problem is called what, sir? Data inconsistency. Data inconsistency. Now question will come, sir, how to overcome this data inconsistency. Now right now if you are observing, sir, where actually we are standing right now, where we are standing, sir, actually try to understand this problem, sir. Why I am explaining this much? The reason is what, sir? Most of the time students don't get the clarity in this. Okay, fine. We are exactly standing here, sir, whatever I earlier discussed to you. So as I said, that critical section is there and multiple processes are trying to access the critical section at the same time, and because of that we are getting data inconsistency issue. Now question will come, sir, how to overcome this data inconsistency issue. So to overcome this data inconsistency issue, sir, we require algorithm. Okay, understood this? Okay, chaliye. So now, sir, and one more thing. Many times students don't have this idea also whether the producer consumer is a normal code or it is algorithm. Whether it is a normal code or algorithm, many times people don't have the idea. Most of the students are thinking that producer consumer is what, sir? Actually a synchronization solution. Algorithm. I say no, it is a normal code where you are getting some data inconsistency issue. To overcome this data inconsistency issue, we require synchronization solution, which will create the effective communication between the producer and consumer. And this is the reason, sir, you are finding in the books also producer consumer problem with what's a semaphore, producer consumer problem with what's a monitor. This kind of statement you are finding. That means what's a normal code. Inside the normal code, we are inserting what actually we are inserting algorithm to create the effective communication. Sir, why you are keeping algorithm, sir? Because I want to avoid this data inconsistency issue, which actually I am finding in the producer consumer case. Understood this, everyone? Okay, chaliye, sir. So let's see this one, what will happen. So these are the few things. In is a variable used by the producer to identify the next empty slot in the buffer. Okay, fine. Out is a variable used by the consumer to identify from where it has to consume item from the buffer. Fine. Count is the shared variable used by the producer and consumer to identify the number of items present in the buffer at any time. Okay. Count is always indicating that the count value is indicating the number of elements inside the buffer. Remember this. Next one, sir. Critical section. Some technicality we'll see. What is the meaning of critical section, sir? It is a shared resource or shared part of a program. Example is what, sir? Example is your in producer consumer problem, we have the count variable and buffer. is an example for this one. Okay, that is a critical section because we are declaring those things globally. So obviously multiple processes will access those two things. Okay, fine. Next one. Cooperative process or coordinating process. If one process is affecting the execution of other process, then these processes are called coordinating processes, else independent processes. The best example is what, sir? Producer is affecting the execution of the consumer, or it may be vice versa also. Okay, fine. So that situation is called what, sir? Cooperative processes. Okay, fine. Next one, sir. Just we have seen, sir, data inconsistency issue. That means they are affecting on each other because of the what, some shared resource. Let's say, sir, what is a race condition? It is a situation where two or more processes executing concurrently and the result is depend on their order of execution. Okay, fine. Let's say, sir, what is the meaning of this one, sir? See here. It is a situation where two or more processes are executing concurrently and the result is depend on the order of execution. For time being, just remember, sir, concurrency means what, sir? At the same time. Here, producer and consumer both are trying to execute the count value at the same time, and because of that, what actually we are getting, sir? We are getting actually two. Okay, so result is depend on their order of execution. If you are finishing consumer in the last, the answer is 2. If producer is finishing its execution in the last, means answer is what, sir? 4. So because we know, sir, whichever process is coming in the last, he is going to become winner actually. It can be producer also, it can be consumer also. It is depend on the which order they are executing. This scenario is called what, sir? Race condition. This scenario is called what, sir? Race condition. Now let's see one example. One more thing. Sir, here he has given the concurrency. What is the meaning of concurrency, sir? Concurrency meaning is very simple. See here, it is something like this. This is the process P1, this is process P2, this is process P3 and process P4, and this is what's the CPU. What is the meaning of concurrency? Sometime CPU is executing some part of the process P1 and some part of the process P2, some part of the process P3 and P4, and once again it is executing some part of the process P1, P2, P3, P4. Once again, P1, P2, P3, P4. Okay, fine. So this mechanism is called what, sir? Concurrency. Concurrency. Okay. Sometime it is executing P1, sometime it is executing P2, like this. This mechanism is called what, sir? Concurrency. Remember, sir, the difference between the concurrency and parallelism. Inside the concurrency, sir, we have the one CPU, multiple processes. And inside the parallelism, sir, we have the multiple processes, multiple CPUs. Remember these points. Okay, fine. Let's say try to visualize this statement of race condition. Okay, still it is not yet finished. Please pay attention to this. What is the race conditions here? If you are observing, sir, as I said, that concurrency means what, sir? See, sometime we are executing producer, and then the first step is what, sir? I have executed producer, then consumer, and this is what, sir? Then producer, and this is what, sir? Then consumer. So exactly this scenario is called what, sir? Concurrency. So as I said, that some part of the process it is P1 is executing, some part of the process P2 is executing, some part of the process P3 is executing. Once again, P1, P2, P3, like this it is executing. Here also, sir, some part of the producer is executing, some part of the consumer it is executing. Exactly this scenario is called what, sir? Concurrency. I can't give better example than this for the concurrency, because you are seeing the concurrency in assembly level also. Pictorially, I have shown you the scenario, the same scenario I'm proving in terms of programming also. This is the meaning of what's the concurrency. Understood this, everyone? Okay, so I will take just one water, little bit water. Okay, fine. So, see, now come to the main points. Come to the main point. Requirements for the synchronization solution. Okay. Requirements to tell synchronization solution is correct or not, sir. As I have discussed, sir. This is the fourth one actually. By mistake, it came here. See here. Anyway, the first one is what's the mutual exclusion, second one is progress, third one is bounded weighting, fourth one is what's the architecture neutral. Okay. So we'll complete this one. Don't worry. So I think within 2 hours of first session, I will complete the synchronization. Okay, I'm trying my level best to complete. Okay, fine. See here. No, it's not your learning first time. You have already learned these things. Okay, let's see next one, because it is a revision class. Mutual exclusion. What is the meaning of mutual exclusion, sir? At any moment, only one process should present inside the critical section. What is the meaning of this one, sir? This is the critical section. This is a synchronization mechanism. Okay, fine. Process P1 is trying to enter inside the critical section. Since no one is there inside the critical section, that's why this synchronization mechanism will allow process P1 to enter inside the critical section. When process P1 is there inside the critical section, at this point of time, process P2 is trying to enter inside the critical section. Then this synchronization mechanism is stopping process P2. So this mechanism is called what's a mutual exclusion. That means Watson, at any moment, only one process should present inside the critical section. This is called what's a mutual exclusion. If you're asking me, sir, what is the opposite word of the mutual exclusion? Then I will say sharing. Sharing. Mutual exclusion means Watson, no sharing. Mutual exclusion means Watson, no sharing. Okay, fine. So just wait for. Chalo, we'll see this one. So hope you understood the what is the meaning of mutual exclusion. Okay, fine. Chalo, progress. We'll see this one. A not interested process should not stop to the interested process. What is the meaning of this one? Okay, fine. We'll see this one. Okay, I'll give you one example for this one. Let's assume this. See, actually, it is my own definition. A not interested process should not stop to the interested process. But in the literature, he has given something like this. The decision about which process will enter into the critical section should made by the other interested process. So that means what's this decision should not made by the other not interested process. So that's why I've taken the definition like this, vice versa definition. A not interested process should not stop to the what's a interested process. That means what's a not interested process should not make a decision about the interested process. If it is happening like this, then progress is not guaranteed. We'll see all of these things. Okay, don't worry. See it. This is your house. Okay, fine. One fine morning, you are coming out from your house because you want to attend the operating system class. The class time is what's 9 o'clock. Okay, 9 o'clock. Now, your name is Mr. X. Your name is Mr. X. And you are coming towards the class, but in the middle of the journey, you found that your favorite hero movie has released. Okay, and the show timing is what, sir? 11 o'clock. And you are a big fan. What is the fan responsibility, sir? First day, first show. Okay, but you know one thing. If you are going to the movie, your other friends will attend the class. So which actually you don't want. So what actually you are doing, sir? You are coming to the class. You are standing out of the class. You are standing out of the class. Okay, fine. See here, and that too also you are standing by 8:30 itself when there is no one is there inside the class. Okay, fine. At this point of time, after some time, Mr. A is coming and is trying to enter inside the class. Then X is stopping to A. He's asking A. X is asking to A, hey, where are you going? Then A is saying, I want to attend the class. So please allow me to go inside the class. Then X is saying, no, you cannot attend. Then A is asking why. Then X is saying, because I am not interested. So you also don't attend. Okay, fine. So now next case. Other person B, he is also trying to enter inside the class. Once again, X is stopping to B. He's asking, where are you going? Then this person is saying, I'm going inside the I want to attend the OS class. Okay, fine. Then X is saying, no, you cannot. Then B is saying, why? Then X is saying, because I'm not interested, so you also don't attend. Okay, fine. So, but what B has done, sir, he slapped X and enter inside the class, Mr. B. So, moral of the story is what, sir? Whether it is a case 1 or case 2, in both cases this X is not interested. But in case 1, X was making a decision that whether A will go or not successfully. Okay, fine. That's why A was not moving forward. But in case 2, sir, X is not making a decision successfully. So B is slapping and entering inside the class. Okay. So that means what, sir, here? In case 1, progress is progress of A is guarantee, sir? Answer is no. In case 2, is progress of B is guarantee, sir? Answer is what, sir? Yes, because a not interested process unable to stop to the what's our interested process. This is the meaning of this one. Okay, fine. Anyhow, so many things I have said about this. Some good stories there, but end of the day, I need to convert into the concept. So which we will see once I'm touching to the algorithm. Bounded waiting. Bounded waiting. Waiting time of the process outside the critical section should be limited. See here. Process P1 is entering inside the critical section and process P2 is waiting outside the critical section. Okay, fine. So how you will check the bounded waiting, sir? You try this pattern. P1, 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 and then P2. If you are getting this pattern, then I will say, sir, bounded waiting is not guaranteed because P2 don't know that when it will get chance to enter inside the critical section. Okay, fine. But if you are not getting this pattern, if you are getting this pattern, P1, then P2, P1, then P2, P1, P2, then I will say, sir, bounded waiting is guaranteed. So here not guaranteed, here guaranteed. We'll check this one. All these things. Don't worry. Okay, fine. Architectural neutral. There is no assumption regarding the hardware. That means you should not say that I have designed one solution. To run my solution, it required this much CPU, this much hardware. Okay, this much main memory, such kind of things. Such kind of dependency should not be there. So that means whatever the algorithm you are designing, it should support to the multiple architecture. Okay, fine. Chalo. We'll see this one. These three are very, very important in the context of the synchronization. Remember this one. We'll see each of this. Now, please pay attention. The first algorithm actually I am discussing is what algorithm we'll discuss, sir? First, we'll discuss two process solutions. Going with great speed and everything, sir. But at the same time, concept clarity is also there. But please pay attention on this. I'm taking two process solution. This is process PI and this is process PJ. Okay. See here. Every algorithm has the two parts. One is the entry section and other is exit section. So this is the entry section, upper side of the critical section, and this is the lower side is exit section. Okay, fine. Now let's see, sir, what will happen. We'll check this one. The first one which we are going to check is what's the mutual exclusion, whether it is guarantee or not. So to check mutual exclusion, because so many stories I have said about the progress and bounded waiting, such kind of things, but here we will prove all those stories. Okay, fine. Now please pay attention to this. First one, I am giving chance to process PI. And I'm taking, sir, turn equals to I. Turn equals to I am taking. Okay, fine. So to prove the mutual exclusion, how you prove the mutual exclusion, sir? Try to bring any one of the process first inside the critical section and check at that point of time any other process can enter inside the critical section or not. If other process is also entering means I will say mutual exclusion is not guaranteed. If other process unable to enter means I will say mutual exclusion is guaranteed. Let's see what is how it is. Okay. See, I am giving chance to process PI. Turn is what's our I? Is I is not equals to I, knows that this condition is becoming false. Process PI is there inside the critical section. Here I am writing. When process PI is there inside the critical section, at that point of time, process PJ can enter or not. So let's check. Process PJ. What is the turn value? So right now it is I. Is I not equals to J? Answer is yes. So this while condition is becoming true. So process Pj will go for what, sir? Busy waiting. So at a time, how many processes are there inside the critical section? One. When process Pi is there at that point of time, process Pj is waiting outside the critical section. So that means mutual exclusion is guaranteed, sir. Answer is yes. So let's see next one. That is progress. Okay. I said that the definition of the progress, a not interested process should not stop to the interested process. Am I correct or not, sir? Fine. So let's see this one. First, you make this one process as not interested, but here I am taking what's a turn equals to J. Okay. So I'm making process Pj as not interested. How can I say that process Pj is not interested, sir? How can I say that? Okay, fine. So remember, sir, whenever process are executing in communication environment, it has the two parts. First one is what's the critical section, other one is what's the non-critical section, and also called as remainder section. Also called as what's the remainder section. Okay, understood this? Chali, next one. We'll see this one. Now, example of this one is, sir, in producer consumer problem, wherever you are finding the count and buffer, sir, that is a critical section actually. Okay, fine. And the rest of the code is comes under what's a non-critical section or remainder section. Example, like produce inside the producer consumer, we have what's a int item p and invariable. Produce item is a function that is also coming what's under non-critical section. Process item, int item p, sorry, int item c and out variable using by what's a consumer. That also comes under what's a non-critical section. Okay, so remember, sir, wherever we have the count and buffer, that is critical section, and the rest of the part is what's a non-critical section. Take. So I am running process Pj inside the non-critical section area. That means what, sir? Maybe it is executing some constant variable declaration. Maybe it is executing some function. You can run process Pj here also if you want. You can run here also. But right now I am very much habituated of running this process Pj here. So that's why I'm taking here. Okay, fine. Now process Pj is running in non-critical section area. That means maybe it is busy executing some other variable or some functions. Okay, fine. Some constant it is executing. At this point of time, I have started with what's the process Pj. It is executing non-critical section area. Okay, this is the first chance. Second chance, what's at this point of time, process Pi, if process Pi want to come inside the critical section, whether it will come or not, sir. Fine, we'll check. And remember, one of the very, very important thing, whenever you are proving progress, the critical section should be freely available. Critical section should be what's up freely available. Okay, fine. Let's see what will happen with the process Pi. Process Pi is executing this one, sir. What is the term value? Right now it is J. If J is not equals to I, sir, answer is yes, then it will go for the busy waiting. That means what's the process Pi will be there inside the busy waiting. Now please try to have some observation. Here, critical section is freely available. Process Pi want to use critical section, but because of the process Pj, process Pi unable to enter inside the critical section. Understood this? How we can say that because of the process Pj only? See here, when this condition is going to become false, sir, whenever turn value is becoming what, sir? J. Sorry, whenever turn value is becoming I actually, I. So the I not equals to I, answer is yes. So this condition is becoming false. But when this turn variable will become I, sir, until unless process Pj is not entering inside the critical section and coming out from the critical section, and if it is setting this turn equals to I, till this point of time, there is no chance for process Pi to enter inside the critical section. Once again, I am repeating, sir. Process Pj is running in the non-critical section area. Process Pi is in the busy waiting because currently turn value equals to what's the J. Question will come, sir. How long process Pi will be in busy waiting until unless this while condition is not becoming false. So when this while condition will become false, sir, whenever turn value is becoming what, sir? I. Sir, when turn value will become I, until and unless the process Pj is not entering inside the critical section and not coming out from the critical section where it is setting that turn equals to I, till this point of time, there is no chance for process Pi to enter inside the critical section. That means what, sir? Indirectly, process Pj is stopping the progress of process Pi or not, sir? Yes, it is stopping the progress of what's the process Pi. Okay, so that means what's the progress is not guaranteed. Okay, fine. So let's see with the bounded waiting. Let's. I need to prove bonded weighting. Okay, fine. What I said to prove bonded weighting, sir, I said this. Try this. PI, and then PG. Lastly. Okay, fine. Let's see whether this pattern is coming or not, sir. Currently, sir, I am taking turn equals to I initially. Okay, fine. Let's see what will happen, sir. Process PI is coming, sir. Is I is not equals to I, sir? No, this condition is becoming false. Process PI is there inside the critical section. Fine, sir. Next one. At this point of time, let's say process PJ is also trying. What is the turn value? So right now it is I. Is I is not equals to J? Answer is what, sir? Yes, true. Then it will go for what, sir? Busy waiting. It will go for what, sir? Busy waiting. Okay, fine. So process PI is there inside the critical section. Process PJ is waiting outside the critical section. Please remember this one. Okay. Whenever you are proving bounded waiting, first ask allow any one process to enter inside the critical section, and at the same time allow other process to wait outside the critical section for this process. Like here, process PI is there inside the critical section. Process PJ is waiting outside the critical section. Okay. So in this way, so here process PJ is waiting outside the critical section. Now follow this pattern. Process PI is coming out from the critical section, setting this turn equals to J, and once again we are asking process PI to re-enter once again. Okay, fine. So what is the turn value? So right now it is J. Is J is not equals to I? Answer is yes. Then it will go for the busy waiting. Then it will go for what, sir? Busy waiting. Process PI, one time it has completed, second time it is going for what, sir? Busy waiting. Okay, fine. If process PI is there inside the busy waiting, let's check with the process PJ. What is the turn value? So right now it is J. Is J is not equals to J, sir? No, this condition is becoming false. Now process PJ, process PJ will enter inside the critical section. That means what, sir? Process PJ will enter inside the critical section. So at a time, how many processes are there, sir? Here, one only. But what pattern you are finding, sir, here? First process PI, then PJ. Okay. And if you are observing this algorithm even closely, so that means what's the bounded waiting is guaranteed, because just I said this. Okay. So next one. So process PI and PJ, it is over. Okay. Chali. Now we'll check another algorithm which is called what, sir? Which is called what, sir? But before that algorithm, we'll see one more thing. In which order process are entering inside the critical sections are PI, PJ. And if you are observing closely, if process PJ is coming out from the critical section, by setting this turn equals to I, indirectly is giving chance to process PI. If process PI is coming out from the critical section, by setting this turn equals to J, indirectly it is giving chance to what's the process PJ. Don't you think, sir? Because of this algorithm, we are creating the effective communication among the process or not, sir? Yes, this effective communication is called what's a synchronization. Okay, in which order they are following, sir? In which order they are entering inside the critical section? Process PI, PJ, PI, PJ. This mechanism is called, not mechanism. This behavior where the process are entering inside the critical section one after the other. This behavior, because of this behavior only, we are naming this algorithm. The people named this algorithm as what's, sir? Strict alteration. Strict alteration. ठीक है चलो. Oh. Now, sir, if anything you want to ask, you can ask. I'm giving you 10 seconds. One hour class is over. One more hour is remain, and after that, 1 hour break is there. And once again, we'll start from 7 to 9. Okay, fine. Check. Next one. So that means no one want to ask anything. Great. Sure. See here. Another one. Just wait for 1 minute. Chalo, we'll see this one. We'll see this one. See here. We'll check what's our mutual exclusion first. Whether mutual exclusion is guarantee or not, sir. Okay, fine. And initially, sir, these flag variables are false. Initially, flag variables are false. Next one. Process PI. So first we are checking the mutual exclusion. Process PI. This is the entry section. And this is what's our exit section. Okay, this is entry section and this is exit section. Flag I values what's are true. Turn values what's are J. Flag J values what's are false. So everything is false. Process PI is there inside the critical section. When process PI is there inside the critical section, at this point of time, process PJ can enter or not. Let's check. Flag J values what's are true. Turn is value what's are I. Next one. Flag I values what's are true. Turn values what's are I. Is I equals to I, sir? Answer is what's a true. Answer is what's a true, because flag I value is true and I is equals to I. So that's why it will go for what's a busy waiting. So how many processes are there inside the critical section at a time, sir? One. So that means mutual exclusion is what's a guarantee. Mutual exclusion is guarantee. Now let's check progress is guarantee or not. Let's check progress is guarantee or not. Okay. As I said, this is what's our entry section. This is exit section. So for the progress, see, first I'm making process PJ as not interested by running this process PJ in the non-critical section area or remainder section area. Okay, fine. Next one, sir. So first I'm proving what's the progress. Okay, fine. So initially, sir, flag values are what? False. Now, when process PJ is not interested, at this point of time, process PI can enter inside the critical section or not. Let's check this one. Flag I values what's the setting this one as true. Turn equals to what's the J. And next one is what's the flag J value is what's the right now it is false. Everything is false. Now process PI will enter inside the critical section. That means what's the though the PJ is not interested, but still he unable to get success to stop to the what's the interested process. So that means progress is guarantee or not? Answer is yes, because you process PJ unable to block to what's the process PI. This is the reason why progress is guarantee. Now let's check with the what's the bounded waiting. Let's check this. As I said that you need to check this process PI, and then PI and then PJ. Okay, fine. So let's see what will happen. Initially, process PI is entering inside the critical section. As I said that both the flag values are what's are false. Okay, fine. So flag I, flag J. Okay, fine. Let's see what will happen. So how you'll prove the bounded waiting, sir? First, allow one process to enter inside the critical section and ask other process to wait outside the critical section. Because the definition of the bounded waiting, what I have given, sir, the waiting time of the process outside the critical section should be limited. Limited होना चाहिए. Okay, fine. So let's see whether it is limited or not, sir. Okay, fine. चलो देखते हैं. Process PI trying to enter inside the critical section. Flag I value is what, sir? True. And turn का value क्या है, sir? J. Fine. Flag J value is what's the false? Everything is false. So process PI is entering inside the critical section. When process PI is there inside the critical section, process PJ, ask process PJ to try. Process PJ. Ask process PJ. Let's see what will happen. Process Pi is there inside the critical section. Flag J value is what, sir? Right now it is true. Turn का value क्या है, sir? I. Okay, fine. Now, if flag I value equals to true, answer is yes. If turn value what's sir I is I equals to I, answer is yes. Then it will go for the busy waiting. Then it will go for what's sir busy waiting. So that means what's sir process Pi is there inside the critical section. Process Pj is waiting outside the critical section. But right now, sir, I am trying this pattern Pi, 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 Pi like this. Then Pj. Okay, I am trying this pattern. Let's see what will happen. Process Pi after some time it will come out from the critical section and it will set this flag value as I value is what's sir false. Next one, sir. Once again, I'm giving chance to what's the process Pi. Flag I value is what's the true. Turn is equals to what's the J. Next. Flag J value is what's the right now it is true. Turn equals to what's the J. Then it will go for the busy waiting. Then it will go for the busy waiting. If process Pi is there inside the busy waiting, because one time it is over, the second time process Pi unable to enter. It is going for what's the busy waiting actually. Okay, fine. So anyhow, I'm stopping here itself. Now I'm giving chance to process Pj. What process Pj is doing, sir? It is checking this. Is flag j equals to true? Answer is what, sir? Answer is what, sir? Flag j equals to what, sir? True. Okay, fine. So it is good. Sorry, it was already in busy waiting. Okay, so process Pi once again re-entering inside the critical section. Because of that, it went for the busy waiting. So flag j is checking this condition. Flag I value is what's right now it is true, but turn equals to what's it is j. So this condition is becoming false. Now process Pj is entering inside the critical section. That means initially process Pi has entered, and after this process Pj is entering. That means they are entering one after the other inside the critical section. So that means what's our bounded waiting is guarantee. Bounded waiting is guarantee. And remember, sir, this is like starvation issue, which you have seen in my classes. If you have seen my classes, okay, fine. So anyhow, so bounded waiting is guaranteed. This algorithm name is what's the Peterson solution. Peterson solution. Okay, fine. So next one. Let's check here one problem. Please read this one. Meanwhile, first you read this one. Don't worry, I will solve data, because if data is there in your mind, everything is good. Or this is a gate problem. Actually, I forgot to write, but I think it is around 2007. I think 7 or 10. Now, so that means these three issues are correct. Okay, fine. Chalo. Let's see this one. Processes P1 and P2 uses critical flag in the following routine to achieve the mutual exclusion. Assume that critical flag is initialized to false. Okay, fine. Chali. So what it is actually asking, sir, it is possible for both P1 and P2 to access the critical region concurrently, or this may lead to a deadlock. We'll check this one, sir. Okay, fine. So what is the first statement? It is saying, sir, it is possible for both P1 and P2 to access the critical region concurrently. That means it is saying indirectly mutual exclusion is not guaranteed. So we'll check whether it is guarantee or not, sir. Okay, fine. And the second one is saying it may lead to a deadlock. Let's check with this one. First, I'm checking with the mutual exclusion. So process Pi is coming. Critical flag value initially what's are false. So it is false. Process P1 is checking. Is this false equals to false? Answer is true. So if condition is becoming true, then we are executing then we are going for the what's the next statement. But before going for the next statement, sir, what exactly happening? I'm preempting process P1 before performing the critical flag as true. Okay, fine. So I've started with the process P1. I have preempted this one. Now I'm giving chance to process P2. Once again, the critical flag value is what's there? Still it is 5 because we have not yet set as a true. So it's false equals to false, answer is true, then it is entering inside the if condition. It is setting this critical flag value. equals to what it is setting, sir? True. Who's setting, sir? Process P2. Now process P2 is there inside the critical section. When process P2 is there inside the critical section, at this point of time, let's see what will happen with the process P1. So whenever process P1 is getting chance to run onto the CPU, it is setting this critical flag value as what's a true one. Okay, and then process P1 is also entering inside the critical section. So at a time, how many processes are there inside the critical section, sir? More than one. So can you say, sir, mutual exclusion is guarantee? Answer is no. So that means what, sir, it is possible for both P1 and P2 to access critical region concurrently. That means what, sir, it is true actually. It is true. Okay, fine. Next one. This may lead to a deadlock. This may lead to a deadlock. Let's check with this one. If you are observing closely, if whatever the process are coming, sir, they are checking the if condition. If it is true, they are executing inside the if. If this if condition is becoming false, then they are coming out from this program itself. They are coming out from this program itself. Okay, fine. So that means what, sir? Whether it is true, if it is true, then they are entering inside the critical section. If it is false, they are coming out from the critical section. In both cases, the process are not getting blocked. But if you want deadlock, sir, you need to block the process. But blocking the process here not possible. So that's why, sir. The first one is true, and second one is what's the false. Understood this? Understood this? ठीक है, चलिए next one. Consider the method used by the processes P1 and P. I think just we have seen this. No, we have seen this one. Go through with this one. Okay, fine. Tell me. Consider the method used by the process P1 and P2 for accessing the critical section whenever needed, as given below. The initial values of shared Boolean variable S1 and S2 are randomly assigned. So please tell me which of the following statement describes the property achieved. So mutual exclusion and progress. Okay, mutual exclusion is guarantee or not, progress is guarantee or not. We have to check this one. Check once. And this is the process P1. Okay. Now check whether mutual exclusion progress is guarantee or not. Just check. I'll come within 30 seconds. So understood this? Let's see this one. Mutual exclusion. This is not a new problem. This is not a new problem. We have already seen this kind of problem. Where, sir? It is a strict alteration problem. Just we have seen a turn variable problem. That problem actually. Okay, fine. Let's see how it is. So mutual exclusion is guarantee or not. So first I'm checking with the mutual exclusion. Okay. So I'm taking S1 is not equals to S2. Okay, fine. So I'm starting with what's the process P1. Process P1 is coming, sir, is checking this one. Is S1 is equals to S2? Answer is what, sir? No. So because S1 is not equals to S2. So this condition is becoming false. Process P1 is there inside the critical section. When process P1 is there inside the critical section, at this point of time, process P2 can enter or not. Let's check with this one. Is S1 is not equals to S2? Answer is yes. Then it will go for what's the busy waiting. That means what's the at a time, how many processes are there inside the critical section? Only one. Busy waiting. So that means what's that? Only one process is there at any point of time here. So that's why mutual exclusion is guaranteed. Let's see with the progress. First of all, I am making one process as not interested. How you will make one process as not interested? Runs out that process in the non-critical section area. You can run above this one also. Okay, fine. Chilling. So, but I am taking initially S1 is not equals to S2, and I am starting with the process P2. I am running process P2 in the non-critical section area like this. Okay, fine. And I am checking whether process P1 can enter or not, sir. Process P1 can enter or not, sir. Okay. Process P. Not checking this condition is S1 is equals to is S1. Sorry, I am taking here. So wrong exception. I need to take this actually. That is a counter example to prove this progress. Okay, fine. Let's see. So process P1 is what, sir? It is checking with this condition. Process P1. What will happen, sir? If S1 is S1 is equals to S2, answer is what, sir? Yes, true. Then it will go for the busy waiting. Then it will go for the busy waiting. Process P1 will go for what, sir? Busy waiting. How long it will be in busy waiting, sir? Until unless this condition is not becoming false. Okay, fine. So when this condition is becoming false, sir, until unless the process P2 is not entering inside the critical section. First of all, process P2 has to enter inside the critical section and come out from the critical section, set this value equals to what, sir? S2 is not equals to S1. Till this point of time, there is no chance for process P1. But right now, process P2 don't want to enter inside the critical section. That means what, sir? That means what? That means progress is not guaranteed, because this process P1 is totally dependent on the process P2 to move forward. Okay, fine. So that's why the progress is not guaranteed. Okay, hope you understood this one. It is not a new for us. We have already seen in the strict alteration. Okay, so that means option A is correct. Semaphore. Let's check with this one. One of the very, very important topic in the GATE. Very important topic. Okay, fine. It is an integer variable which can be accessed by using some atomic operations. Okay, it is an integer variable which can be accessed by using some atomic operation. What is the meaning of atomic, sir? What is the meaning of atomic? Okay, see here we have atomic is what's a non-preemptible. We have one terminology for this kind of things. Atomicity means executing all the instructions without any preemption. It's called atomicity. And atomicity is guaranteed inside the kernel mode. Remember, sir, atomicity is guaranteed inside the kernel mode. Okay, remember one thing. This is user area. This is kernel area. Inside the kernel area, we have the OS. Okay, fine. If any process is running inside the user area, preemption can occur at any point of time. If any process is running inside the user area, preemption can occur at any point of time. It is a universal assumption. Okay, fine. If any process is running inside the operating system, there is no chance of preemption. So such kind of things called what's atomicity. Since semaphore is a part of the operating system, so obviously whatever the operation it is using, that is what's atomic only. That means at the time of execution, it is non-preemptive. Okay, fine. Chलिए it is an operating system resource, because as I said that semaphore is a part of the operating system, so that's why it is the operating system resource. It is invented by Dijkstra, also called as Dijkstra conditional variable. Operations down and up, wait and signal, P and V, the meaning is same. In the different book, he has given the different name, but the implementation wise all are equal. Okay, and next one. See here. Semaphore is classified into two parts. Counting semaphore, binary semaphore. The range of counting semaphore is what's minus infinity plus infinity. The range of binary semaphore is what's 0 and 1. 0 and 1. ठीक है, चलो we'll see this one. The first question will come. First we'll discuss the counting semaphore. Okay, first we'll discuss the counting semaphore. You just read this one. Okay, read this one. Completed. Sure. We'll see this one. Question will come. What is the need for the counting semaphore? If I want to ensure the mutual exclusion, binary semaphore is more than sufficient for me. Okay. See, till now, whatever the example I have taken for the critical section, I said about only what's a count variable. But buffer is also one kind of critical section where we have the multiple partitions. So remember, sir, wherever we have the multiple copies of resource, then we are using what's our counting semaphore concept. The count word itself is indicating that it is going to deal with the multiple elements. Getting this idea or not, sir? So definitely, sir, one buffer has what's a multiple partition. So that's why, sir, we are using what's our counting semaphore. Okay, fine. Chali. Structure semaphore int value q type L. Okay. To implement the semaphore concept, I am taking the structure and it is a integer value. Q type L, I am taking some library function support to maintain the queue. What actually I am maintaining inside the queue, sir? Keeping the blocked processes. Okay, fine. Semaphore S. So if I want to access the element of this structure, I need to define the reference variable. So semaphore S is what's the reference variable. Okay, fine. So see here, S dot value. So I'm accessing what's the integer variable of semaphore, that is value. S dot value equals to 3 and down operation critical section of operation. So this is just template of the what's the counting semaphore. Never ever think that you have completed the counting semaphore. Now we are going to start counting semaphore main. If you want to understand the semaphore operations, sir, you have to understand the implementation of these two operations. Counting semaphore, down operation and up operation. Okay, we'll see each of this. Don't worry. Down operation. Okay, Chili. First you read this one. Over. Chalo, dekh. Normally what is happening, sir? We are just reading this statement. Down means s dot value equals to s dot minus 1. If s dot value less than 0, then block the process, keep in QL. And up means what's the blah 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 blah. This is the first reason why people are not getting the semaphore concept. Okay, why people are not getting the semaphore concept? This is the first reason. To make you simple this concept, let's say something in my way. What is this one, sir? This is a barber shop. Okay, fine. 2 chairs are available. Barber shop. So technically it is called critical section. So let's see what will happen. The first person is coming. Okay, and is performing the down operation. What is the s dot value, sir? 2. Remember, sir, positive value of counting semaphore is always indicating the number of available resources. Here, 2 chairs are freely available, so value is 2. If 1 means what's the one chair is freely available. Let's see what will happen. The first person is coming performing the down operation. Down means what's the decrementation. So it is becoming what's the 1. Is 1 is less than 0? Answer is no. Then simply move inside the shop and have one chair. Another person is coming. He is also decrementing this value to what's the 0. Is 0 less than 0, sir? Answer is what's the no. Then simply move. Okay, move out from the down operation and enter inside the critical section. What is the current value of counting semaphores are 0. So 0 is always indicating that right now there is no resource freely available. 0 resources are freely available, but at the same time there is no block process also. There is no block process also. Okay, let's see third person. Third person is coming and he's what it is doing, sir? 0. Okay, fine. Now it is decrementing this value to what, sir? -1. Is -1 is less than 0, sir? Answer is what, sir? Yes. Then block the process, keep in QL. Okay, fine. Next one. Fourth person is coming, sir. He is also performing decrementation. -2. Is -2 is less than 0? Answer is yes. Then block the process, keep in QL. What is the current value of counting semaphores are -2. If you are asking to come even 100 more, if you are bringing 100 more process also, everyone will get blocked. Okay, fine. So negative value of counting semaphore is always indicating the number of blocked processes, and the positive value of counting semaphore is always indicating the number of available resources, and 0 is indicating right now there is no resource which is freely available, but at the same time there is no block process also. So these many things are there behind this simple down operation, sir. Behind this simple down operation. Hope you understood this one. Okay? Now let's see, sir. After some time, this person one want to perform the up operation. Let's see what it is doing, sir. It is incrementing this value. I will change the color. So up operation, it is incrementing to what, sir? -1. Okay, fine. Now, is -1 is less than or equals to 0? Answer is yes. Then select a block process from the QL and wake up. That means the first person is coming here. Okay, and sitting here. Sorry, the first person is calling to this first person. Please come inside and sit, have my chair because I am leaving. Okay, fine. Next one, sir. The second person is also performing what's the incrementation. The value is becoming 0. Is 0 less than or equals to 0, sir? Answer is what, sir? Yes. Then select a block process person and ask him to visit. What is the current value of counting semaphores are 0? Is there any block processor? Answer is no. Is there any free chair which is freely available? Answer is no. Okay, fine. After some time, third person is performing the up operation. That means I am asking to increment this. This is 1. Is 1 is less than or equals to 0? Answer is no. Then simply move out. The fourth person is also performing what's the incrementation towards the 2. Is 2 is less than or equals to 0? Answer is what's the no. Then simply move out. So if you are observing, when morning Barber has opened the shop, so value was 2. So 2 chairs were freely available. And after that, 4 members came and they performed their own respective tasks. Okay, fine. And they left. So by the time Barber is closing the shop, how many chairs are freely available? Sir, 2 only. 2 only. Understood this? Okay. So remember, as a overall, positive value of counting semaphore is always indicating the number of free resources. 0 is indicating that right now there is no resource which is freely available, but at the same time there is no block process also. Negative is indicating that it is indicating the number of blocked processes. Okay? So next one. Binary semaphore. Okay, fine. Check this one. Read this one carefully. I think it's over for you. Chalo, we'll see binary semaphore. So to implement the binary semaphore, we are taking the help of structure. B semaphore is the name of the binary semaphore. I'm taking here data type as an enum because binary semaphore is accepting only two values, zeros and one, and Q type L to keep the block processes. Semaphore S, so S dot value equals to one. Okay, so it is a what's our by default binary semaphore values what's are one. So this is down operation, critical section, up operation. We'll check each of this. And this is a very tricky one. Please, this pay attention. Full attention you pay. You have to pay. Okay, fine. So we'll see this one. Don't worry. If something is remain, I will after the break I will add to that next session, which is from 7 to 9, and maybe little bit portion maybe remain, whichever actually some problem. So if it is remain, means I will discuss in the next session. But don't think that next section is a main session for the synchronization. The main session is for the memory management actually. Okay, so we'll focus on that. So with this, actually I want to cover synchronization in some up to some good extent, where you should avoid your confusion in the context of the synchronization. I don't want to take the like 1 hour or 1.5 hours. Okay, fine. So we'll see whatever I kept for you. We should complete. I will make sure that I should complete for you. That is okay, fine. So let's see this one. So this initially is a binary semaphore value is what's are one. So by default binary semaphore value is what's are one. Okay, fine. So let's see what will happen, sir, with this. What will happen, sir, with this? When binary semaphore value is one, sir, chair is freely available. Yes, sir. So this is what, sir, this is also barber shop, but it is a poor barber shop. Poor barber shop, where a person, an old person, is sitting behind the tree and performing the shaving and cutting, whatever the task is there. Okay, fine. Chali. The first person is coming. First person is coming. Performing the down operation. S dot value equals to 1. Is 1 equals to 1, sir? Answer is yes. Then setting this value to what's a 0. Okay, fine. And now it is entering inside the critical section. Fine. Chalo. Now please pay attention to this. Current value of binary semaphore is what's a 0. Is chair is freely available? Answer is no. Is there any block process? Answer is no. Getting this idea? Fine. Chali. So remember this point because I will once again recall this point. Okay, fine. Next one. Second person is coming. It is also performing the, it is also checking this condition. What is the is dot value, sir? Right now it is 0. 0 equals to 1, sir. Answer is what, sir? No. Then go to the else part, block the process. Okay, next one. Third person. Okay, fine. So is 0 equals to 1, sir? Answer is no. Then go to the else part. This one. Okay, chalo. Next one. Now please tell me, what is the current value of binary semaphore, sir? 0. How many block processes are there, sir? 2 you are saying after seeing this picture, but can you say, sir, how many block process by seeing the binary semaphore variable value? Answer is no. This is another tricky difference between the counting semaphore and binary semaphore, sir. In counting semaphore, after seeing the variable value as negative, we are saying, sir, let's assume this -3, then I'm saying, sir, 3 block processes are there. But that facility is not in context of the binary semaphore. If you are observing the binary semaphore variable value, the value remains what's a 0 only. When first process is entering also, and after the 2 more process came, the value remains 0 only. Getting this? Fine? Chali. So please remember this one, sir. Now, this first person want to perform the up operation. Let's see what will happen, sir. Is queue is not empty? Answer is yes. Then select a block process from the queue and wake up. That means this first person is saying to second person, boss, please come and sit on my chair because I am leaving. Okay, fine. Now next one, sir. The second person is also checking this condition. Is queue is not empty? Answer is yes. It is asking to come and sit here because I am leaving. Okay, fine. The last one. Okay, fine. He's also executing the up operation. Okay, fine. Is queue is not empty? No, sir. This time it is empty. Okay, this time it is empty. Go to the else part and set this s dot value equals to what, sir? 1. Observation. Which process is setting 1 to 0, sir? First process. Which process resetting this value from 0 to 1? The last process. Getting this idea or not, sir? Getting this? Okay. Remember this one, sir. And remember, very important point. Blocking code is there inside the down operation, whether you are dealing with the counting semaphore or binary semaphore. So beware of this. Okay, fine. Block the process. Inside the up operation, whether it is a counting semaphore or binary semaphore, sir, there is no blocking code. There is no blocking code. Hope you understood this one. Okay. Are you finding any blocking code, sir? here, answer is okay, fine. So blocking is there inside the down operation. That's why we are giving more preference to the down operation while solving problems. Okay, fine. Change. We'll see. Read this carefully. Read this carefully. I'm giving you 10-15 seconds. First, you read. Can anyone tell me answer for this? Chalo. Now read this one. Now read this one. Let M0 to M4 be the mutexes binary semaphore and P0 to P4 be the processes. Suppose each process PI execute the following. Okay, fine. And release wait and release. This could cause. Okay, fine. Let's see what will happen. Whether deadlock and starvation is there or not, such kind of things. Okay. Chali. See here. This problem is very much similar to the dining philosopher problem. Dining philosopher problem. Okay, fine. This is the dining table. 5 philosopher is there. Okay, and 5 binary semaphore is also there. There we have used what's there. What we have used there. There we have used what's in dining philosopher problem we have used folks, but here we are using what's mutexes. And initially, sir, since mutexes are binary semaphore here, initially I'm keeping this. All the things are what, sir? 1, 1, 1, 1. Because binary semaphore value by default it is 1. Okay, fine. Okay, next one. I need to think the deadlock. How to think the deadlock, sir? If you want to think about the deadlock, try to bring all the processes at the same time. What will happen, sir, if all the processes are coming at the same time? They will ask for the resources. If they're asking for the resources, then deficiency of resource will arise, and deficiency of resource may lead towards a deadlock. Okay, fine. Chali, we'll see this one. Initially, sir, all the processes are coming. They're executing this one. So M naught is P naught is executing M naught, and P1 is executing M1. Okay, fine. Next one. So everyone got the left. Next one, sir. Everyone's trying for this one. What is this one, sir? We'll see. 0 plus 1 mod 4 equals to what, sir? 1. So P naught is trying for M1 which is not available block. P1. 1 plus 1 mod 4 equals to kitna? 2. So P1 is trying for M2 which is not available block. In the same way, P2. 2 plus 1 mod 4 equals to 3. Not available block. P3. 3 plus 1 mod 4 equals to what, sir? 0. So P3 is trying for what, sir? M0. Okay, fine. Next one. Okay. So indexing is 1, 2, 3, 4, 5. ठीक है चलिए. Yeah. P4. 4 plus 1 mod 4 equals to what, sir? 1. So P4 is trying for M1 which is not available block. Answer is what, sir? Deadlock. Answer is what, sir? Deadlock. Understood this? Understood this? Okay. Chalo. Go with this one. First, you read this question. Read this question carefully first. Each process PI equals to 1 to 9 is coded as follows. Okay, sir. Repeat forever. Okay, fine. Now, process P1 is executing. First, I will write this code here. Okay, fine. So we'll see maximum how many processes can enter inside the critical section at any time. Okay, fine. So P10 is executing what, sir? It is executing a V of mutex in place of what, sir? P of mutex. That's it. Okay, fine. Chali. So initially, sir, process P1. I am trying with the process P1. Mutex value initially I am taking as a by default value, which is called what, sir? 1. Okay, fine. Now it is performing down on 1. Possible, yes, possible. Process P1 is there inside the critical section. When process P1 is there inside the critical section, at this point of time, if any other process like P2 want to enter, can he enter? Answer is no. Because right now mutex value is what's are 0. So that's why P2 cannot enter. To open the door for the process P2, actually I'm taking the help of what's the process P10. Okay, because this two code are what's the right repeat forever. It is like it is actually Pascal code, but it is like in the C language. If you're asking me, then I will say it is like under the while one, where you are executing the things again and again, again and again. Okay, fine. So P2, P10 is coming and is performing upon mutex, entering inside the critical section, coming out from the critical section. Once again, it is performing 1. Okay, fine. Next one. Now process P2 is getting chance. So process P2. What process P2 is doing, sir? Mutex value is what, sir? 1. So it is setting this one as 0, and the process P2 is also entering inside the critical section. When process P1 and P2 is there inside the critical section, at this point of time, if process P3 want to try, can he enter? Answer is no. Okay, fine. Answer is no. Why? Because mutex value is what, sir? 0. So that's why, sir, that's why to open the door for process P10, process P3, we are giving chance to what's the process P10. So what P10 is doing, sir, it is setting this value to 1, entering inside the critical section, coming out from the critical section, setting this value as 1. Since the current mutex value is 1, you can give easily chance to what's the process P3 also. So P3 is performing down on mutex, and process P3 is there inside the critical section. So in this way, whenever the mutex value is becoming 0, at that point of time, I'm taking the help of what's process P10. Okay, so that's why, sir. That's why. How many processes it will enter inside the critical section, sir? Here 9, and the lastly process P10 will also enter inside the critical section. So maximum 10 process can enter inside the critical section. But as per the given option, answer is D. Answer is what, sir? D. Okay, chali, next. You read this one. You read this. Over. Chalo. We'll see. The following program consists of 3 concurrent processes and 3 binary semaphore. The semaphores are initialized as what, sir? S not equals to 1, S1 equals to 0, S2 equals to 0. Remember, because see, the 10 minutes is left to close this class, but after the class also, I will try my level best to solve some more problem in the synchronization, which will give you some idea about this concept. Okay, fine. It will give the clarity about this concept. It is not just I'm solving 1-2 problem. No, I will solve some more problem. And after that, immediately I will start what? Memory management. Okay, fine. So be ready from 7 o'clock onwards. Okay, chaliye. First we'll complete at least 1-2 problem. If we are solving, it is okay for us. How many time will process P not print 0? It is asking. Let's see how many. Initially, I'm giving chance to process P naught first. So process P naught while true, wait on S naught. Wait on S naught. Okay, chaliye. And it is printing 0. And after this, release S1 and S2. Okay, fine. Next one. After this, I am giving chance to process P1 and P2. So what they are actually doing, they are performing wait on S1, and P2 is also performing wait on S2, and both are performing what's a release S1, release S0 and S0. So that means S0 is becoming 1 and 1 is becoming 1 only here. Okay, fine. Chali. So let's see what will happen, sir. Now, since S0 value is 1, once again I'm giving chance to process P0. So P0 is performing down on S0. Now it is printing once again 0, and it is once again releasing S1 and S2. Okay, but can you process P1 and P2 will execute once again, sir? Answer is no. So this is the difference in the context of the synchronization. Writing code under the while one and not writing the code under the while one. If you are writing any code under the while one, means what, sir? You are executing that code again and again, again and again. If you're not writing the code under the while one, like here, there is no while one. So I will not, this process P1 and P2 will execute only one time. It will not execute in the multiple time. Okay, fine. So in this order, if I am following, sir, I'm getting what, sir? Exactly 2 answer. But if I'm following some other order, let's see how it is. What is other order, sir? We'll see this one. Down on S0, print 0, release S1 and S2. Release S1 and S2. Okay, fine. Next one. Now I'm giving chance to process P1. Wait on S1. Okay. Release S0. Since S0 value is 1, can I run process P0 immediately? Yes. So down on S0 and is printing what, sir? 0. Okay, fine. And once again, it is performing release on S1 and S2. Since P1 has completed, so P1 will not execute one more time. So process P2 I am scheduling. Process P2 I am scheduling. Okay, fine. So what P2 is doing, sir, it is performing down on this one and is performing release S0. So S0 value is becoming what, sir? 1. So once again, if S0 value is becoming 1, means what, sir? I am giving chance to process P0. It is performing down on S0. Okay, fine. And printing 0 and release S1 and S2. Okay, fine. Now please tell me, sir, can P1 and P2 will execute one more time? Answer is no. Can process P0 can execute one more time? Answer is what, sir? It may execute, but it will get block here itself because it's not value is what, sir? 0 here. So that means what, sir? There is no chance that process P0 can execute fourth time successfully, but that means complete execution. It will get blocked here itself. So if I'm following the previous order, then answer was what, sir? 2, and if I'm following this order, answer is what, sir? 3. So best answer is what, sir? Best answer is what, sir? Which is covering these two options is at least twice is the best answer. At least twice is the best answer. Okay, next one. Go with this one. Go with this one. First, you read this one. Over. Let's see what is the meaning of this one. Some more slide is also here. Here, varp and varq are the shared variables, and both are initialized to false. Which one of the following statement is true? It is saying. Okay, fine. So that is deadlock and mutual exclusion. The question is what's the based on the deadlock and mutual exclusion. Let's see how it is. First, I am checking the mutual exclusion. Here, varp is there, and here varq is there. Chalo. Process X. I'm starting with this one. This is varp equals to true. Okay, fine. And now, sir, before executing the next statement, I'm preempting this process. Now, process Y. It is also executing varq equals to true, and before executing the next operation, I'm preempting the process. Okay, fine. Let's see what will happen. Sorry, both the process. Now X is varq equals to true. Yes, sir. Recently we have updated this one. This is true. So it is entering inside the critical section. Now this process is var p equals to true. Yes, sir, we have lastly updated. Okay, fine. So this process is also entering inside the critical section. So at a time, how many processes are there inside the critical section? More than one. Are they satisfying the mutual exclusion? Answer is no. No mutual exclusion. Okay, fine. Next one. Deadlock. See here. Please have some observation. If these two conditions are, if these two while conditions are becoming true, then you are entering inside the body of while one. If it is becoming false, then you are coming out from this body and successfully are moving out. So that means you are not getting blocked in both cases, whether the condition is true or false. In both cases, this is you are not going to get blocked. If you are not getting blocked, means what's how you can be a part of the deadlock? This is the question. How you can be part of the deadlock? Okay, fine. What is the actual mistakes are here? A mistake means I can't say that mistake, but one thing, after the while semicolon is not there. Here directly, since he has not given the semicolon, so everyone is seeing the body, but they are not focusing on the semicolon. So this is the significance of the semicolon, sir. Okay, fine. Semicolon will play a big role in the context of the synchronization. Remember this one. Okay, fine. Check. Next one. This question will take some time. Okay. This question will take some time because chalo, we'll complete. Why we should avoid this one? I'll first complete. You read meanwhile. Three concurrent processes X, Y, Z execute the three different code segments that access and update certain shared variables. Process X execute the P operation. Process X execute the P operation on semaphore ABC, and process Y execute the P operation on semaphore BCD, and process Z execute the P operation on semaphore CDA before entering into the respective code segments. Okay, fine. After completing the execution of its code segment, each process invokes the V operation. Okay, on its three semaphore. All the semaphores are binary semaphore initialized to 1. Okay, fine. Which one of the following represents a deadlock-free order of invoking P operation by the processes? Okay, Chali, we'll see this one. Here we have options here. Read this carefully and tell me which option is the deadlock-free option. Which option is the deadlock-free option? Okay, we'll check this one. Each of this. What is saying, sir? Actually, process X, Y, Z, they are performing down operation on the respective variable, and they are entering inside the critical section, and they are coming out from the critical section, and they are performing up operation on the respective variable. Okay, fine. A, B, C, D. So let's see this one. Process X, Y, Z. All these three processes are coming at the same time. So that obviously down on A, down on B, down on C, they are successfully performing. Now, this one. Can you perform down on B successfully? Answer is no, because B ka value 0. Can you perform down on C successfully? Answer is no, because C ka value 0. Can you perform down on D successfully? Answer is what, sir? Yes. Now here. Can you perform down on A successfully? Answer is what, sir? No. So here deadlock is there. First process getting blocked here. Okay, sorry, here. X is getting blocked on this B, and Y is getting blocked on C, and Z is getting blocked on A. So that means what's our deadlock? Because none of the processes are entering inside the critical section. I will try this one. A equals to 1, B equals to 1, C equals to 1. Down on ABC, if you are observing, sir, down on ABC. Okay, fine. Next one. Now, next column. Since they successfully perform the down on ABC, so they are moving next for next column. Down on A possible? Answer is no. Down on B possible? Answer is no. Down on C possible? Answer is no. So that means what's the deadlock here? Deadlock. Okay, now we'll see, sir, B option. Okay. Let's see whether deadlock is there or not, sir. If you're observing, Z is performing down on A and Y is performing down on B, and the X is getting blocked here itself. Okay, fine. Now these two processes are performing down on C, but any one of the process will perform successfully. So let's assume this Z is performing this one successfully. It is moving forward. Okay, fine. Now, on C, process Y is getting blocked. On C, process Z is getting blocked. Okay, sorry, process Y is getting blocked on C. On B, already X was got blocked. Okay, fine. So let's see what will happen, sir. So Z, can you perform down on D successfully? Answer is yes. Now it is entering inside the critical section and it is coming out from the critical section and it is setting this value as what's ABC as up. Okay, fine. Now please pay attention to this. On A variable, is there any processes blocked, sir? Answer is no. Then it will reset this value to what, sir? 1. Okay. On C, so one variable is blocked, sir. It will unblock this Y process. Okay, fine. And on D, up. On D, is there any process blocked, sir? No, sir. It will reset this value to 1. Okay, fine. So anyhow, sir, Z is over. Now Y is executing. Y is performing what, sir? Since C value 0, why? Because this process Z unblock the Y, so it is moving forward. Now it is performing down on D successfully. It is entering inside the critical section and it is performing up on B, C, D. Upon B, C, D. Okay, fine. Now please pay attention to this. On B, any variable is there, sir? Any process is there, sir? B variable, yes. So it will unblock this one. Down upon C, so it is 1. Upon D, yes, it is setting 1. Okay, fine. Now, since two processes are over Y and Z, I am giving chance to X. It is already unblocked by process Y itself, so it is executing this one. Down on A possible, answer is yes. Down on C possible, answer is yes. Now they are entering inside the critical section, coming out from the critical section. Okay, setting this value ABC as 1 because no other process getting blocked on this. Okay, fine. So which option is correct, sir? Option B is correct. Option B is correct. Understood this? Understood this? ठीक है, चलो. So